Okay, thank you. So the theme of this afternoon, the last talk, is model projections. That's what I was given. I didn't quite know what to do. And my interpretation was that I see that in context of carving and not, I won't give you the full global sea level projection kind of stuff, but anything that I think is relevant to carving or where carving maybe messes up projections. Um, and uh, my work personally, I don't really do predictions or avoid to do that. But you will later see why we sort of got into that. And I think it should rather be Foesa giving the talk, but very happy circumstances didn't allow her to do that. So I jumped in. Well, Olivier forced me to do it, I have to say. I didn't want to. Yeah. Anyway, so this was IPCC 2007, right? Um, you see the predictions they made, and there was a pretty big question mark about the contribution of glaciers, and in particular ice sheets. And yeah, we come to why this was. In general, sort of before 2007, roughly, if we thought about projections, it was mostly about surface mass balance. Stuff is coming on top, it's melting away. This is now a glacier, but it could also be an ice sheet. For the Antarctic, it was, of course, different there. Ice streams were looked at. But this was basically it. So it was very much like a surface mass balance problem. This is just one plot out of Ali's paper in Science 2005. Some prediction of what could happen to Greenland. We have a CO2 scenario, and then you get a sea level contribution somehow. And this model, for instance, was basically driven by surface melt or atmospheric warming, and that was it. And I think we got pretty good in that. There's different schemes, energy balance models, positive degree day models, and it seems like air temperature really sort of scales to melt somehow. There is still issues, but because some models don't agree. But anyway, so in 2007, or just before that, a few years before, things suddenly started to change a bit. We had probably the first one really that was looked at was Jakobshavn, starting to speed up in the late 90s. So this is velocities, you all know that. And behaving rather strangely, losing a lot of mass, doubling its speed, and and this happens in other places as well, all along the coast basically, where you have big outlet glaciers coming in, we have much higher mass loss. Sort of the yellow areas are more the ones that are melting, so still the classic surface melt. And it seems to be related to retreat of these glaciers, not only, but mostly a lot of thinning and so on. So very rapid changes. And you can go along the coast and you find this is a profile along the northwest coast, I think, from the north to the south. A paper by Kier. I quite like it. It's longer time scales. So this is DH thickness change from 1985 to 2010, 1985 to 2005. And the big peaks are basically the outlet glaciers. And most of them seem to do something over timescales like that. So, and down here you can see the retreat, and mostly when you have big thinning, you have quite a lot of retreat as well. So there is kind of a regional picture or a clear picture over longer timescales that, they most do something like that. If you look closer over shorter timescales, these are velocities. Velocity change, 2000 to 2005, 2005 to 2010, and the dots sort of indicate the color, whether they're retreating or whether they're losing mass or flowing faster or slower. And you can see neighboring glaciers might not do the same over these time scales, and also from one period to the next, and they do something quite different. So this one was advancing and then retreating. this one was retreating a lot and not much before. So there's a lot of noise or fluctuations over shorter timescales. And if you look, I quite like this plot from the 2007 paper from Ian Howard, showing mass loss or mass anomaly to the sort of normal case of with time of Kangerlussuaq and Helheim. Just follow the circles here. It's pretty flat, basically zero mass loss, and then jumps up a lot, but it goes down very quickly as well. So, you know, depending where you sample, if it's here or over here, you get a lot of mass loss or you get nothing. So these things change very quickly over very short timescales. And they can also go back again very quickly, as Helheim does, the red circles here. But that's just one episode. And so before the last IPCC, or the 2007 IPCC, there was this question, do we have to rethink everything? You know, the timescales involved are much shorter, things change really rapidly, are we losing Greenland, and so on. So, but at that time, we didn't really know what's going on, and certainly the models wouldn't do it at all. So the models would still sort of do the surface mass balance problem. But actually, we had rather this problem here for these outlet glaciers. I mean, that could be an ice sheet. I might just show it on the tidal glaciers. I think it applies also to our smaller tidal glaciers as well. And I think it's important to go back and think about sort of what do these glaciers do in the future to the early case of Columbia Glacier, where actually they had to ask this question or try to answer this question as well. What is Columbia going to do in the future? At the time when they started their studies, sort of the late 70s, early 80s, they suddenly had Columbia starting to discharge a lot of icebergs, and there was some concern that in Prince William Sound, which is sort of here, going up, Columbia Glacier here, the pipeline, the oil pipeline over there, the ships trying to get there, they were concerned about icebergs, right? So that was why the USGS had to go and study this glacier and figured out a lot of things. And they were asked to sort of make a prediction what's going to happen to Columbia. And they actually did even some modeling. I think there were at least 2, if not 3 modeling studies. And they came up with most of the things we're doing today in some way. But at that time, they were very much limited by computer power and things like that. But I think it's important to realize we tried to, or there's a lot of knowledge from the past as well on the smaller tidal glaciers rather than the Greenlandic outlet glaciers, which we still should use. And I think we learned a lot about the dynamic behavior just from the case of Columbia, maybe other smaller tidal glaciers. I once put this data kind of together. Well, most of it is from Krimmel. I added a few lines. What's important about these tidal glaciers? Well, they're not quite sort of in line with the climate. If you think about retreat rates, they're stuck somewhere for a while, and then suddenly they go very fast. They can have enormous flow speeds, and they're very sensitive to topography. So basically, they're very highly nonlinear systems. And knowing that, I think the problem of addressing this tidal outlet glacier problem, for instance, in Greenland, makes it much harder, and we have to be aware of that. So, yeah, regarding IPCC 2007, we all realize it's a very poor representation of that terminus we have in our models. So how, you know, what are we going to do? And don't follow all the arrows. I think the purpose is it's just enormously complicated. There's lots of feedbacks and everything affects the other bit. And I think the other important part is, which we in 2007, I think we didn't quite appreciate enough yet, is that now this ocean forcing is also an important part, and probably far more important than we thought before. So we don't really represent, or didn't really represent anything like that in our models, and there's technical issues like just spatial resolution, for instance, which I just illustrate here. This is Helheim, and this is sort of a pretty good grid at the time of 2007 IPCC, 5 kilometers. Maybe some could do 2 or so in ice sheet scale models, and you can see, you don't even resolve the fjord, and certainly you haven't got the right bed if you are on that scale. There's also issues like grounding line dynamics. I think there the model has advanced quite a lot. A lot was invested, comparisons, theoretical solutions, and so on. And then, because we know from Colombia, for instance, that these systems are pretty non-linear, and that this non-linearity comes to a large degree from the bed, and there's also an issue that for most outlet glaciers in Greenland, for instance, we didn't have the bed at that time. So maybe Jakobshavn we had a bit, that was it. Helheim, there were about 3 data points which turned out to be not very accurate. So, yeah, I should talk about the projections so far. So, and I move away from that ice sheets for a minute, because for the glaciers we have a similar problem. There, what do? We measure surface mass balances on about 70 glaciers, maybe it's 100 or 150, and then we upscale for the whole world at all glaciers if we have sort of we roughly know the distribution of size and thickness and whatever of glaciers. But the tidewater margin glaciers are actually pretty much ignored in that estimate. And sea level contribution of glaciers is, I think it's even bigger than the one of Greenland currently to sea level, and about the same as well, I think it's about the same as the 2 ice sheets together. But yeah, as I said, we ignore the tidewater margins. And this is a plot of the recent IPCC showing distribution of glaciers in yellow, so non-ice sheet glaciers and ice caps. And these circles here, they show area, how much the size is the area of the glaciated area for these squares here. And then the blue parts show the percentage of, or the ratio of tidewater terminating glaciers. So, I mean, if you go to the Antarctic Peninsula, it's almost all, and this is a big circle. There's a lot up here. So I think just treating glaciers in general as land-based is probably not a very good idea, knowing that the tidewater glaciers are pretty sensitive or can change very quickly compared to land terminating. Right. Yeah, this is straight out of IPCC in the cryosphere chapter. It says, although tidewater glaciers may also be affected by changes in outflow related to calving, the complexity of the associated processes means that most studies limit themselves to assessing the effects of surface mass balance changes. And I wouldn't really know many studies that really treated the calving in a more sophisticated way. And regarding ice sheets, after 2007, we sort of had to do something, because in 2007, the problem just came up. We didn't know what's going on. We didn't understand the processes yet. We didn't have the models. But we kind of promised, well, next time we do better. And I think there were a lot of projects in that said, well, we're going to improve this issue. And so people tried to do something about it, because I think we were expected to do something. 70 years or 6 years is quite a long time. So this was one attempt, the sea rise project. So what could we do? So this was one attempt of projecting to the future. They didn't quite say they make a projection, but they said, well, let's take all the models we have at their current state. They might not have the processes in there, but we can maybe come up with some simple experiments that go in that direction. For instance, crank up the flow speed, right? Let's just increase sliding by 2.5 to mimic kind of these dynamic effects in some way and see what happens with these different models for Greenland. And you can see there's quite a spread. And this I think this is kind of the mean. But you probably all agree, well, we don't quite know how representative this experiment actually is. It could well be that you would have to do that every 10 years maybe to get a realistic answer, or maybe it's far too much. Here this is the case of just increasing ocean melt by 20 meters a year, or setting it to 20 meters a year. Actually, most models didn't actually have ice shelves in where you could actually apply the ocean melt. So I don't quite know how they did it. And the ones that had something in, they fixed their terminus. So none of these models had really moving margins or carving margins in them. So this is very ad hoc, but it gave some sort of an idea maybe how things would respond if we change something. This is a slightly more sophisticated experiment. You know, this is with the Elmer model, much higher resolution. You can actually start to resolve some of these ice streams. But again, you had to come up with some simple experiments saying, well, let's increase sliding by a factor 2, and then this will be the discharge signal. So it increases at the beginning because you, from 1 second to the other, you increase it. But then it sort of slows down with time. You could also increase it sort of every few years or continuously up to 10 times higher, which is this one. This would be the discharge increasing and increasing and increasing. So you can do these sort of, imagine some clever experiments that might relate to somehow reality in the future. And you get some estimates of sea level contribution from the dynamic part. So this was, and then there's another attempt which actually took, again, an ice sheet model. It doesn't really have a moving carving margin, but it looked at the 4 major outlet glaciers and looked what were the thinning rates in the last 10 years or 15 years. What were was the mass loss, adjusted it to that, sort of added that up over time, and came up with sort of these sea level rise contributions from Helheim, Kanger, Jakobshavn. I think it's only the 3 of them. And then additionally, it came up with some upscaling, right? So you take what you get here and you somehow magically upscale to all the outlet glaciers in Greenland. You roughly know maybe how many there are. I think so here, roughly it was a factor of 6 or something. You just multiply this by about 6, I think. But I think it's important that they also added some kind of uncertainty, which is pretty wide. But I think it's important to do that. And one thing to mention here is, and that applies to all of the ice sheet model runs I showed before who tried some sort of future projection, is this initialization issue. You know, somehow you have to bring your ice sheet to the right state where you can start doing your model experiments. And many of the initial conditions, for instance, in the sea rise project, turned out that some had trends going up. If you wouldn't apply any perturbation, they would grow, or they would shrink, or some would just be happy. But certainly it's not a trivial thing. Some had too thick ice, so the surface mass balance turned out to be different later, and so on. So the initialization turned out to be pretty important for what results you actually later got. And I think, what most of the time is done is compare velocity fields or maybe ice thickness, but maybe we should rather look at get the right trends for the initial condition. That's just a thought. But so far, these ice sheet attempts, most of them had really no calving retreat feedbacks in there, so that the calving margin could actually move back and feed back into the flow speed, accelerate. And most of them also had these upscaling. Well, they're not the large scale models, but the smaller, these ones have these upscaling issues. And then there was a very different approach, which I kind of found really interesting, which is turning it round. So there have been some kind of guess or extreme sea level rise predictions. It could be that 2 meters of sea level rise could come from Greenland by a certain time, 2100 or whatever. So that would be the target, or even 5 meters. So when we suddenly discovered these dynamic changes, people were putting some numbers out. And so Tad Pfeffer and some other authors started to think about, well, what would you actually need to get these 2 meters in terms of outlet glacier flow speed increase? I think this is the number for 2 meters from Greenland. You would need an increase of about 50 times the current flow speed to get the 2 meters in 2100. So this seemed a pretty big number, and I think it's quite neat to think, 50 times increase is probably a bit much. I mean, we can't really say it's wrong, but it seems not so plausible. Jakobshavn increased by a factor of 2, a bit more maybe. There's some single glaciers which increased even more than that, but I haven't heard of a 10 times increase or over long time scales. Anyway, if you do 5 meters, it's even more. And then they sort of thought, well, let's say all glaciers would increase by a factor of 2, like Jakobshavn, and then you can estimate what you get from the dynamics. It's 93 millimeters by 2100, I think, which would be a bit more than the surface mass balance. But I think it's quite important to do these sort of exercises. I mean, it's not rocket science, but it might give you an order of magnitude. So the question still was, what is really the dynamic contribution from tidal glaciers in the future? Is it, these 2 meters or far less? And what none of the models before really did is include the fully dynamic treatment, where you have the feedback in that if your terminus retreats, you have some loss of buttressing, it speeds further up, and these dynamic feedbacks were not really in none of the bigger models. So, for Ace and me, we did produce this simple flowline model at the time. We used it to understand actually how these glaciers change. It's more sort of process understanding, test a few hypotheses. We didn't really mean to use it for predictions, but it seemed to be the only model out there that, or maybe we were the only ones that dared to try and apply to real glaciers. Anyway, it's a very simple model we used. It's a flowline model, and I don't go through the details, but basically it includes these dynamic feedbacks. The calving margin can move backwards and forwards, but it's very, very basic. It's a flowline model. It has sort of the basic ingredients, longitudinal stress gradients, basal drag, lateral drag, and it's all balanced by the driving stress. And we use this crevasse depth model in which Doug sort of pointed out that you can stick in several kinds of forcings in a more or less realistic way, but certainly you can tweak some of the forcing, we think, into carving. And then we applied that to the 4 major outlet glaciers, where we actually had bed topography. That was one limitation why we did it there. But, you know, it's 4 different models, kind of, and we represent the glacier basically by a line in the middle, roughly, and it has a width, so the width is in there in some way as well. But the 3D representation, of course, is kind of limited. And then we had to put in the forcing somehow for the carving thing here. So ocean forcing, what does the atmospheric changes do to it? And this just sort of summarizes roughly where things go in. And that was sort of based on our best understanding and some sensitivity experiments. But it's simple parameterizations, right? It's basically you have maybe surface melt, ocean melt. So we take some subsurface ocean temperature from a big model. It's the ocean temperature further out, so it's not even in the fjord. And we sort of have a factor that puts it up and down, and it increases submarine melt or decreases it. So just by scaling it in that way. We use the crevasse water level and linked it to surface melt or to runoff. But again, you shouldn't think that this is really the physical process, but it's one way to put that in. We have basal lubrication linked to runoff. We also play with lateral resistance on the sides of the outlet glacier, and we link that to air temperature and runoff. And then this was sort of to mimic the ice melange type, used SST and sea ice. And these are the 2 scenarios we tested. And the input data for that came from the regional climate models. So this is just sea surface temperature, deep ocean temperature, so that's out in the ocean, right? That's not in the fjord. But anyway, we just scale that in. Surface runoff, and then we have fjord air temperature, so this is just air temperature, atmospheric force. And we used this period here, about 10 years or 15 years, to calibrate our model. So we match, for instance, terminus positions, Helheim, Kangerlussuaq, Jakobshavn. So all the colored lines are different model runs. And we did a whole lot of them. I think it's about 50 for each glacier. So we played with all the different parameters in the forcing. And then the cyan, this light blue line, that's the observations here as well of terminus position. Here I can hardly see it. Oh yeah, there it is. There it goes. So we try to roughly match that. And this was not, I said that before, you know, we didn't have a root mean square error estimate of how well we match it. This is basically sort of look at it and think, well, yeah, does a pretty good job. We get the general trend. Okay, that's the main thing we wanted to have. And roughly the seasonal signal. Here we get the seasonal signal pretty well. Here we get, again, the general trend, the seasonal signal, perhaps a bit less good. And what you also wanted to match is the actual fluxes. So the ice flux, because we want to look at how does the ice flux change. We need to know, we need to make sure that the ice flux is roughly right. And what you see here is for different years, I think. Yeah. These are the observations on this side for different years of front velocities. So this is at the calving front, this is upstream, and you can see that's the model results. Not too bad. We roughly represent this sort of speed up and shape of flow speed. For Peterman, things were slightly different. This was the one that was hardly sensitive to any forcing at the ice tongue. It was only sensitive to basal lubrication, basically. What you see here is observations. This is the red one is after the big iceberg broke off, and you can see there's hardly any speed up compared to October 2009 before the break off. And this one is a summer measurement. And so by applying basal lubrication linked to air temperature, we could pretty much mimic what was being observed. So we had basically, based on about 10 years of data, we had a model that roughly behaves as it should. And from that, we already learned quite a few things based on the parameterization we used and the calibration, that some glaciers are sensitive to certain things and less sensitive to other things. So Peterman, sensitive to ocean melt, or more sensitive to ocean melt and facial sliding, whereas Helheim seemed to be more sensitive to our ice melange air temperature forcing. But again, these are just sort of in our parameterized world, right? And we didn't quite know the details how to do that. And if you imagine, for instance, Peterman, if the ice tongue would retreat in 100 years, then maybe its sensitivity would change as well. But it's calibrated on the present state. Yeah?
The model has a width.
Yeah.
That appears in the ice flow as the lateral.
That appears in the mass conservation, basically the surface. Lateral drag as well. Yeah.
The same width?
No, not necessarily. There's places where it's the same width when it's out in the fjord, but upstream it's not the same. Yeah, because well, to get the mass in, you need the full basin, and with lateral drag, not necessarily. Anyway, so we had that model, and we learned quite a bit about the sensitivity of the different glaciers to our parameterization of forcing. And then we used the two warming scenarios, or this is a quite extreme one, 4.5 degrees warming by 2100. And this is sort of the normal global mean warming by about 3 degrees by 2100. We used the model projections of climate models. What were they called? If you want to know, well, there you go. It's the MAR mainly for the atmosphere, and then the ECOM 5 for the ocean for the projections. Anyway, big scale mode. And this is what comes roughly out. This is just a A1B scenario for the different glaciers. In red, you see the geometry. It goes from dark red to light red with time over about, I think it's 100 years. And in green, you see the velocities with time, from dark green going to light green. I think what is important here to see is that you get, for some, you get very episodic behavior, right? It's out here for a while, then it's stuck here for a long time, and then it's stuck here for a long time, but in between it doesn't really stay anywhere. You see how things speed up quite a lot. So this is, I think it's kilometer per year scale. This is Helheim here as well, rather episodic. So phases of very rapid retreat and thinning, whereas Peterman is more sort of gradual, and in this case it's actually dominated by the ocean warming and ocean melt, the retreat, and it gets stuck. And if you think about the sensitivity of tidewater glaciers or calving to bed topography, you also see that, kind of see that in here a little bit. It gets stuck where it's shallower, but it's not always that obvious. Here it seems pretty obvious. Here, it's an upslope, so in a way stable. But this location, for instance, or that one is not so obvious. And some of that has to do with the width, that in some places like this, the glacier is pretty narrow. What else do I have to say here? I think what you can see as well here is during the whole retreat, even if it gets into pretty deep stuff, the speed at the front doesn't just go to infinity, certainly not to 50 times faster, right? It's sort of, the 12 kilometer per year and so on. There might be short time periods where it's quite a bit higher, but I haven't plotted such a high time resolution, so you can't really see it, because these times are very, very short when it's very fast. So we have, this is just the older scenario, the glaciers retreat a bit further. Now, in terms of mass loss, it's really the flux that is important. And I think that's quite an interesting plot. It shows the flux in gigatons per year of the different glaciers with time for the A1B scenario. And you can, I think what is the striking thing is the flux sort of is up here, and it goes a bit up sometimes, but it doesn't just go to infinity or so. It sort of seems to level out at some point. So the acceleration, the extra mass loss, doesn't just continue to go up and up and up and up. I think that was quite important to get out of this. There's periods where you lose a lot of mass very quickly, but these periods are pretty short. And then it's sort of quiet for a while, and then maybe you have a few more peaks. Down here, for Petermann, the real increase only comes later when I think the ocean melt has removed basically the ice cone, and then you get higher mass fluxes. So here, the mass loss really kicks in quite a bit later. But they don't just go up and up and up. If you would have, extrapolated sort of the last 5-10 years of mass of outlet glacier acceleration, you might have come up with something like this. And I think some people did that, and I find that quite unfortunate, because it doesn't seem to go to. So it rather seems like the scenario of Tap-Pfeffer of, let's say, they all speed up by a factor of 2, seems not to be so far off. If you do the other scenario, the more extreme warming scenario, the fluxes are quite a bit higher, and there's also some higher peaks as well. So it's not that it can't go higher, but I think it doesn't just continue to go up and up and up. And that, in a way, makes sense that if you speed up things, you also need to put mass down to your terminus, that you actually can discharge it. So you can't just keep increasing at the infinite rate. And these are the cumulative mass change. The black lines are the dynamic contribution, the red ones are the surface mass balance contribution. Surface mass balance comes directly from the climate models. And surprise, surprise, for Helheim and Congalusa, they're actually positive. I think that's the reason is that there's hardly any ablation area, because in East Greenland it goes up very steep. And if it gets warmer, you get more precipitation. And I think that's what that signal is. But again, a line sort of doesn't go like this, right? This is cumulative mass loss. It sort of is pretty gradual, apart from Petermann, which doesn't do much initially and then goes like that. And these are, again, I just show here 5 parameter set runs, or an ensemble of 5 runs with slightly different parameter settings for the forcing. But they all roughly match the observations in the first 10 years pretty well. And this is what you then, in the end, get in terms of dynamic contribution. So this is time, contribution to sea level rise, and that's the envelope of all the experiments, basically. and then that's the surface mass balance contribution. And in blue, no, the blue is the dynamic, sorry, and in black is the total. So for these 4 glaciers, the dynamic contribution really dominates. But I think you have to be very careful to upscale that, because these guys have basically no ablation area, so they're not representative for the whole of Greenland. The surface mass balance for other areas will go much more up. And the yellow one is just the other scenario. So, and I've got to say, in that data, of course, there's no surface mass balance altitude feedback. So, as the glacier thinned down the surface, the climate model doesn't know that. So it's just static, taking the old surface. So there would be extra melt from that. But important is, things are not accelerating forever. And I mean, when I looked at that first, I was surprised how linear this is. It just goes up like that. And if you think about your outlet glaciers going crazy for a few years and then not doing much, I was kind of surprised. But this is probably the average you get. And the peaks are very short. So in a way, it seems like we get something quite simple. And maybe there's the hope that with a simple model you can actually, or with some very basic equation, you can actually come up with something like that. Anyway, enough of that. Oh, no, no. Yeah, so for the 4 major glaciers, we got about, for the A1B, I think, this were the numbers, 10 millimeters contribution. And then, from the mass loss, I'd say that later. Anyway, here, we then had to kind of scale up to Greenland, and we really didn't want to do that. But, you sort of are almost forced to do that, because people want to know, what's the contribution of Greenland then? And we, in the paper, really said this is not a good idea to do. Or you have to be very careful. But we basically multiplied, because they cover about 22% of the area, or the flux, and we multiplied by about 5 and came up with this estimate. We got from the climate model the surface mass balance, and this was the total kind of for the A1B scenario. So 6 to 15 centimeters by 2100, I think this is. And that was a number. And then you could go back to all the other numbers of the other estimates and see how that compares, and actually it doesn't compare too badly. So anyway, there's big limitations in this study. The 3D effects are not really in there. I mean, there's a bit of variation in width, but that's it. Surface elevation feedback is not in there. The forcing we put in was kind of, you calibrate, you do the best you can to match the observations and then hope behaves the same in the future. And the upscaling here is certainly not recommended. But that's another issue I have. How can we do that better? Because I think we can't get around that. Particularly if we want to look at all the tidewater glaciers, not the ice sheet ones, and upscale mass change there. We somehow have to do it. From that on, Gölzer used basically our retreat rates from the flowline model and stuck it into an ice sheet model. And to get kind of a better idea about the 3D effects of thinning and how that propagates and what additional mass loss you get. And he could include, of course, the surface mass balance altitude feedback. So he then got, from just the dynamics, he got about the same numbers as we did, which probably makes sense. And I would have been surprised if they would have been very different. I think something would have been wrong. But for the whole ice sheet, he only got about 20% from dynamics, right? So this basically says, well, maybe the dynamics ice sheet wide doesn't matter too much because there is a lot of melt on the Greenland ice sheet, and a big area is basically exposed to melt. And I think one important, interesting thing he figured out was the dynamics and surface mass balance kind of compete each other. Dynamics itself had an increasing effect on the surface mass balance because it lowered the surface down, so you get more melt. So the dynamics gets less important, kind of. And you can, this is just a slide from Tony from last week he gave me, and this is basically the only study I can think of that really tried to put in a dynamic ocean terminating calving front, and we get that number, and the other ones sort of tried to come up with scenarios or did some other estimates, and these are these numbers here. And you know, they're not so far off. Order of magnitude. But in terms of, yeah, they're probably much less constrained in the calving sense. And then coming away from Greenland, because most of it what I showed was Greenland, this is a study that tried to project the change of Columbia Glacier to the future. And I think it's quite a neat way, or maybe an additional way of doing things. He used the Monte Carlo ice flow modeling approach, where he had a lot of data, of course, Columbia Glacier. So we have a lot of data. So he had several parameters to force things, and he could test the sensitivity of them. And out of a whole load of model runs, he would figure out which ones are the ones that are okay. And then he also got a whole ensemble of different parameter settings he could do. And this is basically what he did. This is the retreat position. So it was still advanced here, then it started retreating. These are the observations. It matches pretty well. In gray, you can see the model runs. There's a whole load of them. And the black line, I think, is the mean. So, you know, he would reproduce it quite well. And these are the flow speeds. I think this is the discharge with some measurements here. But of course, to do that, you need a lot of data in the first place to kind of train your model or constrain your model. And you can't really do that in places where you haven't got much data. And also, as you get to the future, things get probably more and more uncertain. Because your glacier might not be in the state anymore where it actually was constrained initially. So it could have all sorts of surprises. So this is basically what IPCC 2013 said about ice sheet rapid dynamics. Are we confident? Well, sort of medium. So maybe we improved compared to the first one because this was basically excluded at all in the IPCC 2007. So, in a way, some improvement. Now, I haven't talked about Antarctica yet, and I have to do that quickly, I think. This is maybe a bit provocative. Antarctica seems to be easier in some way. There are general big ice shelves, and as Doug pointed out in the study of Ian Joggin, calving is not included most of the time, but it maybe doesn't matter too much for some of them, at least for thwaites, because it's just sticking out. And also the troughs are much, much bigger, right? You can actually resolve them, even in a low-resolution ice sheet scale model. But I think it's important to point out that almost all of them don't really deal with the calving. They just melt things away by ocean melt by some pretty high numbers. And so they actually don't have to deal with the calving. in many of these studies. I won't go into detail here. This is just another one, Pine Island, model comparison. Yeah, they get quite different results. The pattern seems similar, probably mostly controlled by the bed topography. And this one is one which came out just recently. This is a study of the East Antarctic ice sheet, or part of it, with the basin below sea level. They did a whole load of runs to figure out, the stability. And there seems to be some sort of, either it's stable, half stable, or it goes all the way back here. And this would be a lot of ice lost. And they have this eigen-calving law. And you can say, well, yeah, maybe it's not a very well-defined law. There's a parameter in we don't know, and so on. But at least they had a try in sort of putting in some calving model to look at what the effect then is. And the crucial thing here is this ice plug, this sort of relatively small floating ice tongue, or grounded in parts, that plays a crucial role whether the ice sheet is out here or here. If the ice plug is there and big enough, it's stable. If it's not there, it goes. And it just illustrates again this high non-linearity. Right, so to sum up, I think from all the observations, and you probably all know that, these outlet glaciers, calving glaciers can change very quickly. So extrapolating changes is probably not a very good idea. Although when I saw our result, the overall mass contribution, it seemed all quite a nice line. So maybe we can do it, I'm not sure. In terms of the calving models, whatever we used also in our flowline model, it's still very crude. And all the models I think we're using are pretty crude. For the big ice sheet models, they probably have to be. They don't really include the 3D effects well. Maybe damage is really something that one could put in, even on potentially on an ice sheet scale. And I think here, how we put the forcing that affects calving into the models is not clear. I mean, we just sort of, had some factors in there and parameters in there which we put up and down. But I think here we need to understand things much better in order to do that. The initialization problem is still there, which affects really the results to the future. And then I think what really we're missing is that we haven't really validated any of these models. And I don't quite know how to validate a calving model, because you're not measuring calving as such. You're measuring kind of how the glacier changes at the back, how it retreats, and so on. So benchmark data sets are certainly important into comparative studies. And the other thing is, if we think about IPCC, the 10-year calibration and then extrapolate for 200 years, it's maybe pretty dangerous. And we didn't really, I would say we did the calibration, but we never really did the validation as such. And so how can we validate over longer time scales? We need longer time scale data as well. And it might not have to be that much, but a few data points in earlier times. And then also, I said that before, come up with strategies how to assess model performance, whether it's a good model or a bad model or okay model. We need the forcing data, and for the oceans this is particularly difficult, but I think the paleo record might help in the long-term data set. And then we need the bed geometry, because everything seems to be pretty sensitive to that, but we won't get it for all the glaciers in the world. So we need to come up with some clever ideas how to deal with that and upscale to the world if you think about sea level contribution. And then, I mean, I guess the models, they keep improving all the time. people come up with some really good new models and put in more physics. The spatial resolution on an ice sheet scale will probably still be an issue for a long time. This, I'm not sure whether we actually, in the large scale models, should ever start doing. I guess we have to study it on a small scale, come up with parameterizations that work, and maybe use them. Okay. I have some last messages, I think. Yeah, oh, there's a mistake. This means projections. So I think we should also not expect to predict every glacier exactly when it retreats and does its big catastrophic event. We should start thinking in these average ensemble kind of retreat responses, and maybe some kind of minimal models as Jeremy showed today. Earlemans did some stuff as well that don't need that too much data, but roughly do the right thing, might be helpful. And this is just to warn you that it's not just Greenland. There is a lot of other tidewater glaciers, which some of them have quite a bit longer data sets available than we have from Greenland. Yeah, and this is a more provocative question. Do we want to, or do we dare to do projections? Should we do that? Or is it too dangerous? Or shall we focus first just on the process studies and understand everything first? I think the expectation from our funding agencies and IPCC is we should do something like that. But I think doing it parallel is probably the best thing, but we have to be careful what we say here. I agree to that. Okay?